I would like to apologize for any background noise, but starting off with number 13, or question 13, um, the question states that the rate law of reaction can only be determined from experiment. Two experimental procedures for determining the rate laws were outlined in this chapter. What are the two procedures and how are they used to determine rate laws? So the two methods to determine rate laws are the methods of initial rates and the integrated rate law method. So an easy way to tell that you need to use the method of initial rates is when you're, kind of self-explanatory, but when you're given initial rates, but um, it might yeah, it might look like something like this, like in the table, or maybe it's given to you in like word problem form. But so the way you find the rate law using initial rates is you divide um two initial rates. So like for example here in this example problem or table, you would divide rate 2 over rate 1, but you would also have to divide the concentration of A, A2 over A1, which is shown here. And you would use this formula to find M and also N, but you would also do the same thing for rate 3 and rate 2, as well as B3 and B2. I think it's self-explanatory, but then you plug those numbers into uh, the formula, or you plug, like for example, you get 0.1 from the concentration of A, and then you would also have to do the same to B, because these correspond, and the M is the N and the M are the exponents. But then you would solve for K to get your rate constant, and then that's how you get your rate law. And for the integrated rate law method, um sorry um so for example, this question reads, a certain chemical reaction follows first order kinetics. The decomposition of gas X into products is monitored over time. The concentration of X starts at 0.8 moles, and after 120 seconds it drops to 0.2. How much time will it take for the concentration to drop to 0.05? So you can solve this by using the formula. So this formula right here. So basically, you have your values in the problem, or maybe table, or whatever's given to you, and you just plug them in. So you get the initial, and you plug that in, and you get the final, and then your time, which is 120 seconds. And so you would have to solve, so in this problem you have to find time, but in order to do that you need to find concentration first, or not concentration, K, the rate log constant. So you would solve that, and then you can make a rate law from that. Or if you have a problem like this, then you can use whatever you get here as K to find T. But moving on, number 20. Hydrogen reacts explosively with oxygen. However, a mixture of H2 and O2 can exist indefinitely at room temperature. Explain why H2 and O2 do not react under these conditions. So, the hydrogen and oxygen would only be able to react if they formed new bonds, but the first they would have to break apart like the hydrogen and oxygen bonds to make new ones, but they're pretty strong, so you would need a lot of activation energy to do that. So, you could do this by raising the temperature, the room temperature, or like heating it up, or maybe providing a different source of energy, like maybe fire or anything. But um, then for question 42, the following data were obtained for the gas phase decomposition of dinitrogen pentoxide. Define the rate as negative delta N2O5, the concentration of N2O5 over delta T. Write the rate law and calculate the value of the rate constant. So in this problem, they give you the initial rates. So you would use the initial rate law method shown in question 13. But so you could do this by just getting rate 2 and rate 1 and the concentration of N2 and N1, or N2O5 1, but you plug in the values and you solve for M, and by doing this, solving for M, you can, I'm sorry, um, I'm sorry, so now that you have M, you can find the rate constant, and you would plug it into here to find K. So you solve for K and you get this, but you also have to remember sig figs, because this is also important, which would give you 0.0119. And this would also be the rate law. You just use it as K. And okay, so moving on to 79. So in order to complete 79, we first need to do question 39 so that we can get the rate law from that. So the reaction 2NO plus Cl2 creates 2NoCl. Was studied at negative 10 degrees Celsius. The following results were obtained. What is the rate law and value of the rate constant? So again, here you see that we get the initial rates. So I'm sorry. So you would want to do rate 3 and rate 1, and you can solve for M that way. And you can do the same thing with rate 2 and rate 1 and solve for N. And with that you can with that you can use this formula to find, because you would plug in M into the coefficient, the exponents, the M and N to the exponents, and since N is 1, then it's just 1. You don't really have to put anything there. But you take the rate from here, and then you put it there, and then you solve this and you get K, which would be 180. So, but that also gives you the rate law with M and N of rate is equal to K, and so here's the rate law. But so for question 79, it is asking, is the mechanism consistent with the results obtained in question 39? If so, which is the determining step? So now that we've done 39, now we can answer this question. So we can assume that step 1 is fast and at equilibrium, and that step 2 is slow. So first we can make the rate law for, we have to try and make the rate law for step 2 to try and compare it to the other rate law from question 39. And um, but we also have to put it in terms of reactants, since NOCl is a intermediate because it's produced here but then used here. And since we're looking for the rate law, we have to move um, so we just have to solve for the rate law. So since it's an intermediate, we would put it into here, the reactant form, or how you would do it, and that would create this by solving that. You put NOCl onto this side and K on that side, since you're trying to get into rate law, the rate law form. You need K on the right side with NO and Cl, but um, um, so then we can simplify what we have by combining the two NOs here. So we have one here and one here. So we don't really need to have them separated. We can combine them into NO squared. And by comparing the rate law that we have here and like simplifying it, then it's the exact same as the one from question 39. So that means that um, they they do correspond, and that um, and that, well, we know that set 2 is the determining set because we got the rate law that matches question 39 from step 2. But yeah, that's basically it. So thank you.